The Embraer E190 has a retractable tricycle landing gear system with 2 main landing gear assemblies and 1 nose landing gear assembly. The main landing gear assemblies are telescopic and retract sideways into the wing and fuselage. Each main landing gear assembly incorporates 2 wheels with multi-disc carbon brake assemblies. The nose landing gear assembly is telescopic and retracts forward into the fuselage. The nose landing gear assembly incorporates 2 wheels with a hydraulic nose wheel steering mechanism, allowing the aircraft to turn on a taxiway as narrow as 17 meters. During normal operation, the landing gear system is electronically controlled and hydraulically operated. Several proximity sensors are installed to provide position and status signals to different electronic modules, located in the Modular Avionics Units, or MAU, for control and monitoring purposes. The sensors also display system status to the pilots via the ICUS display in the cockpit. The following equipment is installed in the cockpit for landing gear extension and retraction. The landing gear control lever for extension and retraction of the landing gear during normal operation. An extension override switch is used to extend the landing gear in case of a failure in the landing gear electronics, and a manual release lever used for freefall extension of the landing gear in case both the electronic and electrical systems fail. The cockpit equipment for steering the aircraft includes a steering handwheel, steering pedal sensors, and disarming switches on the control yokes. 2 brake pedals for the left and right main landing gear brakes are installed for both pilots. An emergency parking brake handle mounted on the center pedestal allows for braking even in case of a total hydraulic system loss. An optional automatic braking system can be engaged by the crew by selecting the respective auto brake switch in the cockpit. The main landing gear assemblies are attached to the left and right wings. The assemblies include 2 wheels with brakes attached to a telescopic shock strut. A folding side stay holds the main landing gear in the fully extended position. A locking stay holds the side stay in the fully extended position. A pair of down lock springs hold the locking stay in the extended and locked position. Proximity sensors transmit the following signals to the Proximity Sensor Electronic Module, PSEM. Main landing gear down and locked. Main landing gear up and locked. And aircraft on ground, also referred to as weight on wheels. During retraction, a hydraulic release actuator unlocks the locking stay. A hydraulic retraction actuator retracts the main landing gear. The uplock holds the main landing gear in the retracted position. There are 2 doors attached to the outboard side of each main landing gear. A 3rd door is attached to the wing. The doors are mechanically opened during extension and closed during retraction. The nose landing gear assembly is attached to the forward fuselage. 2 wheels and a hydraulic steering motor are attached to a telescopic shock strut. A folding drag brace holds the nose landing gear in the fully extended position. A locking stay holds the drag brace in the fully extended position. A pair of downlock springs hold the locking stay in the extended and locked position. Proximity sensors and switches and feedback sensors transmit the following signals to the Proximity Sensor Evaluation Module and the Nose Wheel Steering Control Module. Nose landing gear down and locked. Nose landing gear up and locked. Aircraft on ground. Nose landing gear steering angle and nose landing gear steering over travel. During retraction, a hydraulic release actuator unlocks the locking stay. A hydraulic retraction actuator retracts the nose landing gear. The up lock holds the nose landing gear in the retracted position. Two mechanically operated doors are mounted in the fuselage on each side. The forward doors close again as the nose landing gear reaches the extended position. There are three modes of landing gear operation available to the crew: normal extension and retraction, electrical override, and mechanical freefall. In the normal extension and retraction mode, the landing gear actuation is electronically controlled and hydraulically operated. The landing gear selector valve is controlled by the Proximity Sensor Electronic Module, PSEM. The landing gear selector valve provides hydraulic pressure to the actuation cylinders. In the electrical override mode, the landing gear extension is electrically controlled and hydraulically operated. The extension override switch takes direct control of the selector valve. The Proximity Sensor Electronic Module is removed from the control loop. In the mechanical freefall or emergency extension mode, the landing gear extension is mechanically controlled and gravity powered. Pulling the cockpit manual release lever mechanically releases all landing gear uplocks and activates the freefall selector valve. Gravity and aerodynamic forces will then extend the landing gear. A total of 6 wheels and 6 tires are installed on the aircraft. The 4 main landing gear wheels are equipped with electronically controlled and hydraulically powered carbon composite brakes. The brake control system uses electronic modules, sensors, and hydraulic valves to control the aircraft brakes for normal braking mode. And it has an optional auto brake mode. 2 brake control modules, or BCM, and 1 optional auto brake control module, ABM, control the hydraulic pressure to the inboard and outboard brakes. With the auto brake switch in the cockpit selected on, the ABM will apply the brakes automatically after landing and following a rejected takeoff. The anti-skid control system prevents wheel skid when the brakes are applied. The emergency parking brake system allows brake operation even with a loss of hydraulic pressure. A brake temperature monitoring system monitors actual brake temperature and provides temperature status and brake overheat warnings to the crew via the ICAS. The nose landing gear of the aircraft can be steered by the crew to allow for directional control of the aircraft on ground. The crew commands the steering system by using either the steering hand wheel for low-speed steering control, allowing for a steering angle of up to 76 degrees, or the rudder pedals for high-speed steering control, limiting the maximum steering angle to 7 degrees. The system is electronically controlled and hydraulically actuated. The nose wheel steering control module, NWSCM, controls the steering hydraulic system and provides input to the hydraulic steering motor installed on the nose landing gear. There are 2 modes of operation: normal mode, or active steering, and free caster mode, or passive steering. The normal mode allows the crew to actively steer the aircraft using either the steering hand wheel or the rudder pedals. In the free caster mode, the nose landing gear steers in response to external forces applied, such as rudder movement, differential braking, or towing. The position and warning system incorporates 2 identical proximity sensor electronics modules, or PSEM. Various system proximity sensors, such as weight on wheels or landing gear up and down lock sensors, are connected to the PSEM. The PSEM controls the extension and retraction of the landing gear and indicates position of the landing gear system, the ground spoiler system, and the aircraft doors. The nose wheel steering control module in WSEM controls the towing lights. The towing lights provide a visual indication of whether towing is allowed. The maximum allowable steering angle is monitored by an over-travel proximity sensor on the nose landing gear shock strut. In case the maximum towing range has been exceeded, a steering over-travel target will be sheared off. As a result, on the ICUS, the caution message, landing gear, no dispatch, will be indicated. The PSEM also controls the air-ground system. Proximity sensors on the nose and main landing gear, referred to as weight-on-wheel sensors, sense whether the aircraft is on ground or in flight. Weight-on-wheel sensor status is distributed to various aircraft systems via the ASCB. The landing gear system of the aircraft uses Hydraulic System 1 and 2 to perform the various functions. Hydraulic System 3 is not used. Hydraulic System 1 provides hydraulic pressure for the following systems: main landing gear braking, outboard wheels; main landing gear braking, emergency parking outboard. Hydraulic System 2 connects to the following systems: main landing gear and nose landing gear extension and retraction; main landing gear braking, inboard wheels; main landing gear braking, emergency parking inboard; and the nose landing gear steering. The main landing gear shock strut carries the fuselage while the aircraft is on ground. It consists of the main fitting, the sliding tube and axle assembly, and the torque links. The main fitting and the sliding tube together operate as a spring and damper, or shock absorber, reacting to the loads and aircraft movement during taxiing, takeoff, and landing. The folding side stay consists of an upper and a lower part, and supports the main landing gear in the extended position. The upper part of the side stay attaches to the wing structure, and the lower part to the shock strut. A two-piece locking stay locks the side stay in the extended position and folds it during retraction. Two proximity sensors are attached to the locking stay. They transmit a signal to the PSEM when the main landing gear is down and locked. Weight-on-wheels sensors attached to the upper part of the torque links signal aircraft on ground to the PSEM. The shock strut includes the following main components: the main fitting, the sliding tube and axle assembly, the torque links, and the shimmy damper. The main fitting is the primary structural element of the main landing gear. It has an uplock roller and attachment lugs for the side stay, locking stay, retraction actuator, main landing gear doors, and upper torque link. It is attached to the aircraft via pintle pins. The sliding tube and axle assembly has attachment lugs for the lower torque link and the jacking dome. The torque links prevent wheel rotation around the sliding tube axle. Steel targets are attached to the upper torque link for the weight-on-wheel sensor. A shimmy damper is installed between the upper and lower torque links to reduce shimmy at any speed. The main landing gear shock absorber is a double-acting oleopneumatic telescopic shock strut. The shock absorber is filled with hydraulic fluid, MIL H5606, and nitrogen. The lower chamber is filled with nitrogen and fully isolated by a fixed piston. The upper and middle chambers are filled with hydraulic fluid. When a shock absorber absorbs the shock, the nitrogen is compressed and the sliding tube moves over the fixed piston. Oil then flows through metered holes at the top of the sliding tube and in the fixed piston into the oil chamber inside the ram of the fixed piston to absorb the energy of the shock. After this, the compressed nitrogen expands and thus causes the shock absorber to expand again. The main landing gear shock strut can be serviced through the hydraulic filler valve in the middle of the strut housing. The charging valve for nitrogen is in the bottom part of the sliding tube. It is not necessary to jack the aircraft for hydraulic or nitrogen service. There is also no need for any special tools. For maintenance, the shock absorber has static and dynamic spare seals. Note, a clean sliding tube will extend the life of the dynamic seal significantly. The side stay is a two-pieced hinged strut that holds each main landing gear in the fully extended position. The upper part is attached to the wing structure by a hinge pin, and the lower part is attached to the shock strut, also by a hinge pin. The two parts are connected with a hinge pin. The locking stay is also attached there. The two-piece locking stay locks the side stay in the extended position. The upper part is attached to the shock strut, the lower part to the hinged connection of the side stay. For maintenance and ground handling, a ground safety pin can be installed into the locking stay. The locking stay is unlocked hydraulically by use of a downlock release actuator. Each main landing gear assembly consists of 3 doors: the upper door, the middle door, and the lower door. The doors are mechanically opened and closed during extension and retraction of the main landing gear. The upper door is attached to rib 4 of the main landing gear box in the wings. Rods from the main landing gear main fitting attach to the upper door, pushing the door open during extension and pulling it closed during retraction. The middle door is attached directly to the main landing gear main fitting. The lower door is attached to the middle door, and rods connected to rib 4 of the main landing gear box in the wings. During extension, the rods push the lower door open to provide clearance for the full stroke of the main landing gear shock absorber. During retraction, the rods pull the lower door closed. The nose landing gear shock strut supports the forward fuselage while the aircraft is on ground. The nose landing gear shock strut assembly includes the main fitting, a sliding tube and axle assembly, a steering motor, and the torque links. The main fitting and the sliding tube together act as a spring and damper, and react to loads and aircraft movement during taxiing, takeoff, and landing. The steering motor turns the sliding tube and axle assembly for nose landing gear steering on ground. Centering cams on the sliding tube and main fitting hold the steering in the 0-degree position whenever the aircraft is not on ground. The drag brace consists of an upper part attached to the fuselage and a lower part attached to the shock strut. A two-piece locking stay locks the drag brace in the fully extended position. A downlock safety pin can be installed when the aircraft is on ground. The nose landing gear shock strut includes the following main components: main fitting, the sliding tube and axle, the steering motor, and the torque links. The main fitting is the primary structural element and includes an uplock roller and attachment lugs for the drag brace, the locking stay, the retraction actuator, upper torque link, and nose landing gear doors. It is attached to the aircraft structure by pintle pins. The sliding tube fits into the main fitting. The sliding tube includes the wheel axle, a towing adapter, and attachment lugs for the lower torque link. A jacking dome is installed for nose gear jacking. The steering motor and a towing light indicator are bolted to the main fitting. The nose landing gear shock absorber is a double-acting actuator type designed to absorb kinetic energy. The shock absorber has 3 chambers. The lower one is filled with nitrogen. The 2 upper ones are filled with hydraulic fluid, MIL H5606. The function is similar to the main landing gear shock absorber. During the initial compression, the nitrogen is compressed, and then hydraulic fluid from the upper chamber is forced through all calibrated holes into the middle chamber. To extend the shock absorber again, the backflow of oil into the upper chamber is limited through fewer holes, since the spring-loaded damping valve is forced to close. This assures a slow extension. The nose landing gear shock absorber also has spare seals. Servicing the hydraulic fluid and nitrogen is performed through the filling and charging valves. The main fitting has a spare seal activating valve. This valve can isolate the main seals in case of a leakage. The activating valve is located in the lower portion of the main fitting, adjacent to the lubrication fitting. When the activating valve is closed by maintenance action, it switches the hydraulic pressure from the main seals to the spare seals. The main landing gear incorporates a similar system with a different installation. To activate the spare seals, follow the detailed instructions as mentioned in the Aircraft Maintenance Manual Part 2, MPP. The drag brace is a 2-piece hinged strut, which keeps the nose landing gear in its fully extended position. It is attached to the aircraft structure and to the shock strut by hinge pins, and has an attachment lug for the downlock release actuator. The locking stay is attached at the hinge point between the 2 parts of the drag brace. The other end of the locking stay is attached to the main fitting of the shock strut. The 2-piece locking stay locks the drag brace in the extended position and folds it during retraction. The locking stay locks mechanically in an over-centered position and can be secured in this position by a ground service pin. 2 downlock springs force the locking stay into the over-centered position, which guarantees safe locking in case of spring failure. 2 proximity sensors are installed on the locking stay to transmit a signal to the PSEM when the nose landing gear is down and locked. Unlocking the locking stay from its down position is accomplished hydraulically using the downlock release actuator. The steering motor is used to rotate the nose gear for maneuvering the aircraft on ground. The steering motor has 2 hydraulic cylinders attached to a geared rack. The geared rack meshes with the circular gear on the main fitting. Hydraulic power from the steering manifold can move the rack, which will then rotate the circular gear. This rotation is transferred via the torque links to the sliding tube and axle assembly. A towing light box is also installed on the main fitting with 2 lights. If the green light is on, towing is permitted. If the red light is on, towing is not permitted because either the steering motor, the brakes, or parking brakes are pressurized. Further details will be described in the steering section. Four doors that are attached to the forward fuselage are mechanically opened and closed as the nose landing gear extends or retracts. The rear doors are connected to the main fitting by means of a rod, pushing the door open during extension and pulling it closed during retraction. The forward door mechanism incorporates a series of rods and cranks, causing the doors to open during nose landing gear extension and then to close again as the nose landing gear reaches the fully extended position. During retraction, the forward doors are opened until the nose landing gear reaches the fully retracted position, and then close again. To open a nose landing gear forward door for maintenance purposes, remove the quick release pin and release the translating nut from the telescopic rod. Then, move the door to the open position. To close a nose landing gear forward door, move the door to the closed position and torque the translating nut, then install the quick release pin on the telescopic rod. The extension and retraction system of the landing gear is made up of a number of subsystems for system operation and control, either under normal, abnormal, or emergency conditions. These systems are the electrical control, monitoring and indication system, the landing gear hydraulic system, and the two emergency extension systems, electric override and freefall. Normal extension and retraction is requested with the landing gear control lever located on the co-pilot's instrument panel. The extension and retraction sequencing is then performed by the proximity sensor system, PSS, which incorporates two proximity sensor electronic modules. The PSEMs get inputs from the LDG control lever and from several proximity sensors of the LDG. The LDG hydraulic system receives power from the hydraulic system number 2. It contains the necessary valves and actuators to perform the operations required from the electrical control circuit. The main components are the LDG selector valve, the uplock boxes, the downlock release actuators, the LDG actuators, and the freefall selector valve. If the normal extension fails, the landing gear can still be extended by using an electrical override switch. The PSS control system is then bypassed and the LDG extension solenoid is directly controlled. If the electrical system is not available, a pure mechanical system, the freefall system, can be used to extend the landing gear. In this situation, the freefall selector valve and the uplock actuators will be moved mechanically. All hydraulic lines will be connected to return and the landing gears will extend by freefall. The main landing gear retraction actuator is a double action type with internal restriction devices. The cylinder housing is attached to the wing structure. The non-adjustable actuator piston rod is attached to the main fitting of the landing gear. The actuator is used to extend or retract the landing gear by hydraulic pressure from the landing gear selector valve. The speed of the actuator movement is controlled by restrictors in the hydraulic outlet port for either extension or retraction. The nose landing gear retraction actuator is similar to the main landing gear retraction actuator. 3 separate uplock boxes are fitted to the aircraft structure for uplocking of the main and nose landing gear. When the respective landing gear is fully retracted, the uplock roller on the shock strut is engaged by the hook of the uplock box. The uplock box is a hydromechanical unit. The locking action is performed mechanically. The unlocking system can be actuated either electrically and performed hydraulically for normal and electrical override extension, or actuated mechanically for emergency freefall extension. 2 proximity sensors are installed on each uplock box. These sensors send the uplock signal to the PSEMs when the landing gear is up and locked. The main landing gear downlock release actuator is a double-action cylinder with an adjustable piston rod. The cylinder housing is attached to the main fitting of the landing gear, and the piston rod is attached to the locking stay. During extension, the actuator is forced to extend by the movement of the landing gear, since both lines of the downlock release actuator are connected to drain. To retract the landing gear, the downlock release actuator has to overcome the spring force of the downlocking springs and remove the locking stay from its over-centered position. Therefore, hydraulic pressure is directed from the landing gear selector valve through the retraction line to the piston. The cylinder will retract and unlock the landing gear. The nose landing gear downlock release actuator is installed between the locking stay and the drag brace. The function is the same as the main landing gear downlock release actuator. The landing gear control lever is installed at the cockpit central panel and is used to command the landing gear extension and retraction. The position of the lever is sensed by microswitches, which are connected into the PSEMs. A mechanical locking device prevents inadvertent movement to the up position while the aircraft is on ground. A solenoid-operated electromechanical device releases the locking mechanism, allowing the lever to be moved to the up position with weight off wheels. In case of a control system or solenoid failure, a red override push button in front of the control lever panel allows mechanical release of the locking mechanism when pressed.
Steering, we have nozzle steering control module.
The landing gear selector valve is installed. A check valve is incorporated into the return line of the landing gear selector valve. It is a spring-loaded poppet valve that opens if pressure rises above 5 psi. It will avoid backflow in case of a pressure peak from the system return line, which assures that no inadvertent command will be sent to an uplock box and release the landing gear. The landing gear selector valve is installed in the fuselage. It sends hydraulic pressure to the extension or retraction side of the landing gear hydraulic circuit in order to move the landing gear up or down. The valve is an electrically controlled 3-position 4-way valve. If both solenoids S1 and S2 are de-energized, the spool valve will be held in the center position by the 2 springs. Pressure is blocked off, and all landing gear lines are connected to return. If the PSEMs energize solenoid S1, hydraulic pressure from the pressure port will move the spool valve to the right, and pressure will be directed to the landing gear downside to extend the landing gear. If S2 is energized, the pressure will force the spool valve to the left, and the hydraulic pressure can then retract the landing gear. The Proximity Sensing System, PSS, provides the control and position indication of the landing gear. In addition, the PSS provides weight on wheel, spoiler position, door position indication, and steering over travel monitoring. The PSS consists of 2 proximity sensor electronics modules, PSEMs, installed in the MAUs. PSEM1 is installed in MAU1, and PSEM2 is installed in MAU3. The PSS receives position information from the microswitches in the landing gear control lever and prohibits movement of the control lever with weight on wheels via the landing gear control lever unlock solenoid. The landing gear selector solenoid valves are controlled by the PSEMs. Information from each gear is directed from the uplock, downlock, and weight on wheel proximity sensors to the PSEMs. Finally, the PSEMs send the status information of the gears to the ICUS for indication. For system redundancy, each PSEM can control landing gear extension and retraction fully independent of the other. To retract the landing gear control lever has to be selected to up. Hydraulic pressure can pass unrestricted through the freefall selector valve to the landing gear selector valve. The PSS energizes solenoid S1 and the valve will move to direct hydraulic pressure to the LDG uplines. The retraction side of all retraction actuators and downlock release actuators will be pressurized. Due to the smaller volume of the downlock release actuators compared to the retraction actuators, they will move first, unlocking the 3 gears. Then the retraction actuators move the gears up until they lock in the uplock boxes. When the up and locked position is sensed by the uplock proximity sensors, the PSS de-energizes the solenoid S1. The landing gear selector valve will then move to the neutral position and all lines connect to return. To extend the landing gear selector needs to be moved to down. Hydraulic pressure can pass unrestricted through the freefall selector valve to the landing gear selector valve. The PSS energizes solenoid S1 and the valve will move to direct hydraulic pressure to the landing gear downlines. The extension side of all retraction actuators and uplock boxes will be pressurized. Due to the smaller volume of the uplock box actuators compared to the retraction actuators, they move first, unlocking the 3 gears. Then, the retraction actuators move the gears down until they lock in the over-centered positions. When the down and locked position is sensed by the downlock proximity sensors, the PSS will de-energize the solenoid S1. The landing gear selector valve will move to the neutral position and all lines connect to return. In case of control system or hydraulic system failure, a mechanically operated freefall system can be used to lower the landing gear. This system includes the following main components: the freefall selector valve, the manual release lever and forward quadrant, the main landing gear quadrant, nose and main gear uplock boxes, and the connection cables. Gravity and aerodynamic forces are used to extend the landing gear. The freefall selector valve is installed in the lower stub main box. It is a 5-way, 2-position hydraulic selector valve that can be manually activated via the control lever. In the normal or non-actuated position, pressure can pass through the freefall selector valve and all other lines are blocked off. When actuated, the valve connects all landing gear hydraulic lines to return and closes off the pressure line, allowing unrestricted extension of the landing gear. The manual release lever is located in a recess in the cockpit floor on the right-hand side of the center pedestal. A door is open to obtain access to the lever. To pull the lever up, a safety button has to be pressed to prevent inadvertent movement of the lever. The lever is connected via a rod to the forward quadrant, which is then connected via a closed loop cable to the main landing gear quadrant. Another cable is directed from the forward quadrant to the nose landing gear uplock box. From the main landing gear quadrant, a cable is directed to each main landing gear uplock box and a rod to the freefall selector valve. To extend the LDG with the manual system, the LDG selector must be selected to down. Pull the manual lever up to an angle of 62 degrees. This will rotate the forward quadrant and via the closed loop cable, the main landing gear quadrant as well. The freefall selector valve is moved by the rod from the main landing gear quadrant and connects all hydraulic lines to return. The uplock hooks in all uplock boxes are mechanically forced to open by the cables. The landing gears are released from their uplock and extend by gravity and aerodynamic forces. The downlock springs force the locking stays down to lock the gears in the over-centered position. Even in freefall gear extension, one downlock spring is sufficient to lock the gear. An alternative way to extend the landing gear in case of electrical command failure is the electrical override system. An electrical override switch is located beside the manual release lever on the right-hand side of the center pedestal. When this switch is selected, 28-volt DC from the essential bus 3 is sent directly to the extension solenoid of the landing gear selector valve, bypassing the proximity sensor system. Hydraulic pressure is directed through the landing gear selector valve, unlocking the uplocks in the uplock boxes and extending the gear via the retraction actuators in the same way as in normal extension. The brake system installed in the Embraer E190 incorporates a main brake system and an emergency and parking brake system. 2 brake assemblies are installed on each main landing gear. The main brake system is a brake-by-wire system, controlled by 2 brake control modules called PSEMs. The outboard brakes are hydraulically powered by hydraulic circuit number 1, the inner brakes by hydraulic circuit number 2. The system provides differential braking capability to steer the aircraft in case of steering system failure. Therefore, the left brake pedals activate the left main landing gear brakes, and the right brake pedals activate the right main landing gear brakes. The brake control system has the following functions: pedal command braking, anti-skid protection, pressure control, touchdown protection, locked wheel crossover protection, gear retract braking, built-in test and communication with the MAU. An optional auto brake system can be installed. As backup for the main brake system and to safely park the aircraft, a full mechanical brake system is installed, the emergency and parking brake system. It is activated and controlled mechanically with the emergency park brake handle on the center pedestal. It is powered by both hydraulic systems and has 2 dedicated hydraulic accumulators. Pressure to the brakes is regulated through the emergency parking brake valve. The emergency and parking brake system does not make use of the brake control modules or any other control valve or hydraulic line of the main brake system. The brake temperature is monitored by the Brake Temperature Monitoring System, called BTMS. Brake temperature and system status and failures are indicated on the MFDs and ICAS. In addition, the brake control modules supply failure information to the CMC that can also be used for brake system tests. The brake control system has the following main components: 2 cockpit brake pedal assemblies, which include 1 brake pedal transducer, LVDT, for each pedal. 2 identical brake control modules, PSEM-1 controlling the outboard brakes and PSEM-2 controlling the inboard brakes, and 1 optional auto brake module, all located in the MAUs. There are 2 brake shutoff valves, supplying or isolating hydraulic pressure to the brakes, depending on the operational situation, and 4 brake control valves, 2 for the inboard, 2 for the outboard brakes, to regulate the hydraulic pressure. 4 pressure transducers provide hydraulic pressure signals to the brake control module. 1 hubcap-driven, axle-mounted wheel speed transducer per wheel transmits wheel speed signals to the brake control module. 1 optional auto brake switch located in the cockpit selects the various auto brake modes. The brake control system uses volumetric fuses, located on the brake control valve outlets, to prevent a total loss of hydraulic fluid if there is a hydraulic line rupture, or if a failure in one of the components results in a hydraulic leak. Each fuse closes automatically and incorporates a manual reset lever. Check valves are installed on the hydraulic return lines to prevent the flow of fluid in the wrong direction. Shuttle valves downstream of the emergency parking brake valve allow either normal or emergency parking brake pressure to activate the brakes. These shuttle valves are installed at the rear part of the brake assemblies. The emergency and parking brake control system makes use of the following main components: an emergency park brake handle in the cockpit to control or set the system, one dual emergency parking brake valve, two hydraulic fuses, one in each outlet of the emergency parking brake valve, two parking pressure switches, one for the outboard and one for the inboard parking brake for cockpit indication. Via the shuttle valves, main brake or emergency parking brake activation is selected at each brake. Two accumulators can supply pressurized fluid to the emergency parking brake valve. The main brake activation is proportional to the displacement of the pilot's or co-pilot's brake pedals in the cockpit. The position of the pedals is sensed by four linear variable displacement transducers, LVDTs, one dedicated to each pedal. For redundancy, each LVDT is a dual sensor with a primary and secondary winding to sense the position of the movable core. The windings are excited by the brake control modules, which can calculate pedal position via the feedback signal. To prevent inadvertent brake application, an internal spring is installed in the LVDT, forcing its core to the neutral position. Two brake control module controlled main brake shutoff valves are installed at the forward wing stub. Each brake control module will control its onside three-way two-position solenoid-operated brake shutoff valve. When de-energized, the pressure port is closed. The main purpose is to isolate faulty hydraulic components. The secondary purpose is to select shutdown air mode. The shutoff valve will be de-energized closed by the PSEM when air mode is established, or energized open when ground mode is established. The shutoff valve status depends upon the following inputs: weight on wheel status, landing gear selector lever position, wheel speed, and velocity reference, throttle lever position, and brake pedal position. A pressure transducer is installed in each of the four hydraulic pressure lines downstream of the hydraulic fuses. The transducer is a hermetically sealed silicon pressure capsule-mounted type transducer. The silicon capsule converts the pressure in an electrical signal that is transmitted to the respective brake control module. The transducers are positioned in the rear wing-to-fuselage fairing, close to the wheel well. The brake control modules use the signals for the closed-loop pressure control to control the brake control valve in relation to actual delivered pressure sensed by the transducers. Two brake control valves are installed at the wing stub. One valve controls and modulates pressure to the inboard brake system, and the other to the outboard brake system. The brake control valve is a dual two-stage pressure-controlled servo valve. The first stage develops hydraulic control pressure proportional to input current from the brake control module, and the second stage then supplies the related first stage controlled pressure to the brakes. If the brake pedals are fully depressed, the armature in the first stage will close off the return port and system pressure can move the second stage spool valve to deliver full system pressure to the brakes. With no input current to the armature will close off the pressure port, and the spring in the spool valve will move the spool valve to cut off any pressure to the brakes. Brake pressure can be modulated at any intermediate position of the servo valve and in relation to the spool valve to allow different brake forces. A wheel speed transducer is installed in each main landing gear wheel axle. The transducer has a stator and a rotor and self-contained bearings. As the wheel is turning, the rotor is forced into rotation by a clip inside the hubcap of the wheel. The output frequency varies directly with the wheel speed and is sensed by the related brake control module, which processes the signal for the use in the anti-skid, locked wheel protection, and spin-up override system. The volumetric hydraulic fuses are installed at the wing stub area. One is installed in each brake line downstream of the brake control valve. They prevent the loss of the hydraulic fluid in case of a leakage in the hydraulic brake lines or at the brakes, and limit the quantity of hydraulic fluid that could hit the hot brakes. The fuses measure the flow and velocity passing through them. In case of a hydraulic leak behind the fuse, the pressure drop will cause the flow and velocity to increase. This will cause the fuse to close. The manual bypass lever on the fuse can be used to reset the fuse after it is activated, and to bypass the fuse to allow brake system bleeding without inadvertent fuse activation. 4 check valves are installed in the hydraulic return lines. 2 are installed in the return line of the main brake system, and 2 in the return line of the emergency parking brake system. All of them should prevent any back pressure to the brakes by allowing flow only in the direction of return. Also, 2 check valves are installed in the supply lines to the emergency park brake accumulators to prevent discharging of the accumulators when no supply pressure is available, assuring sufficient pressure for emergency parking brake activation. 2 identical and interchangeable but independent brake control modules, PSEMs, are installed in the MAUs. PSEM1 controls the outboard brakes and is located in MAU1. PSEM2 controls the inboard brakes and is installed in MAU2. The 2 PSEMs do not communicate to each other. Each PSEM contains all the circuits necessary to perform the control, monitoring, built-in test, component interface, fault isolation, and indication for 2 wheels. It also incorporates the circuits required for communication with the aircraft indication system, and for maintenance and troubleshooting purposes. The built-in test will check the internal circuits of the brake control module, and almost all associated components in the brake system which receive or send signals to the PSEM. For system redundancy, PSEM1 is powered by DC Essential Bus 1 and PSEM2 by DC Essential Bus 2. Inputs of the following components and sensors are processed in the brake control module: the cockpit pedal sensors, the pressure transducers, the wheel speed sensors, hydraulic systems pressure status, thrust lever input, LDG lever position, air ground status, main gears down locked status, initiated test request from the CMC. In turn, the PSEM generates signals to the shutoff valve, the brake control valve, the ground spoiler system, the thrust reverse system, the nose wheel steering, and the CMC and ICUS. Pressure to the brakes is controlled through the pilot's and co-pilot's brake pedals. When the brake pedals are depressed, the pedal LVDT position is sensed by the brake control modules, which modulate the brake pressure via the brake control valves. The PSEMs perform closed-loop pressure control on the 4 wheels with use of the main brake system pressure transducers. The system controls brake pressure to each pair of inboard or outboard brakes to ensure equal load, energy, and wear sharing during taxi near the brake application threshold. By depressing only the left-hand or right-hand brake pedal, the PSEM will supply brake pressure only to the selected side brakes to allow steering by differential braking. An anti-skid system provides maximum brake efficiency with minimized tire wear and optimized braking distance. The PSEM provides anti-skid protection when the wheel speed is above 10 knots. The wheel speed for the anti-skid system of all 4 wheels is measured by the axle-mounted wheel speed transducer and processed by the brake control modules. This wheel speed information is used to determine incipient wheel skid conditions. A correction signal, the anti-skid command, is generated by the PSEM according to the wheel skid condition to release brake pressure on the individual wheel through the brake control valve. Whenever the wheel speed is above 30 knots, the locked wheel crossover protection will be armed. For this protection, the inboard wheels are paired together and the outboard wheels are paired together. Locked wheel crossover compares the wheel speed of a wheel with its paired wheel. If the wheel speed of the wheel is 33% or less of its partner wheel, then a locked wheel condition is declared by the brake control module. And brake pressure to the locked wheel is fully removed by selecting Return. Locked wheel crossover protection will be disabled when the faster wheel speed is less than 30 knots. When the gear retracts, the main wheels have to be stopped by the main brake system. The brake control system supplies 300 psi through the brake control valve for 4 seconds to all 4 brakes. Whenever the weight on wheel inputs indicate air, the gear handle input transitions to up position and the gear down and locked input is not active. The nose wheels are stopped when they hit a stop inside the nose landing gear bay. To prevent brake actuation during landing with the aircraft still airborne, the touchdown protection is available. To assure that the touchdown is not performed with locked wheels, this protection permits pressure only 3 seconds after ground mode has been established by the signals of the weight on wheel switches, or if spin-up override will allow braking. Spin-up override allows braking when wheel speed of above 50 knots is detected. Spin-up override will also establish ground mode and will override touchdown protection. At 10 knots, the spin-up override will reset automatically. Both touchdown protection and spin-up override work on an individual wheel basis. The 2 shutoff valves are used to isolate the brakes. On ground, with weight on wheel and thrust lever below 80%, the SOVs are energized open by the PSEMs to allow brake control over the full travel of the pedals. With thrust lever above 60% and pedal position above 20%, the shutoff valves open, while if the brake pedal position is below 10%, the shutoff valves will be de-energized to close. After liftoff, the shutoff valves will be energized open for gear retract braking and will be closed after a 10-second time delay when the wheel speed and reference speed are 0. The gear handle is not down, and weight off wheel is detected. As long as the aircraft is in flight, the brakes remain isolated by the de-energized shutoff valve. Prior to landing, when the landing gear selector is set to down, the 2 shutoff valves are tested automatically by a pressure pulse test. The brake control modules energize the shutoff valves and apply a pressure of 600 psi. This change must be verified by the transducers. Then, the brake control modules shut off the pressure command and again de-energize the shutoff valves. The shutoff valve will be energized to on when weight on wheel is detected and the thrust lever is below 80%. The touchdown protection logic prevents brake application prior to touchdown protection, weight on wheels plus 5 seconds, or wheels spin up. The brake control system includes 3 different types of built-in tests. Power-up or event-initiated tests, which are performed every time power is supplied to the system as part of the system initialization, or when the power has been interrupted for more than 50 milliseconds or after a predetermined event. For example, energization of the shutoff valve after a gear down cycle. Periodic tests, which are performed repeatedly, concurrently with normal brake control functions. Operator-initiated tests, which are performed in response to specific requests. All initiated tests are executed only if all wheel speeds and velocity references are 0. Weight on wheel is indicated and low pressure is available. The tests are performed by the brake control module initiated by CMC. If a failure in the brake control system occurs, it will be indicated on the ICUS, with additional failure information available on the CMC. The brake left-hand fail caution will indicate that the left inboard and outboard brake failed. As the right inboard and outboard brakes are available, unequal brake force will be applied. The brake left-hand fault advisory indicates that either the left inboard or outboard brake has failed. The brake pedal left-hand seat fail indicates left and/or right LVDT failure on the pilot side. The same messages are available for right-hand side failures. The brake control fault advisory indicates that one or both wheel pairs are operating with open loop pressure control because of single or double pressure transducer failure. Both brake control modules supply the CMC with further failure information. The auto brake system installed on the Embraer 170 and 190 family aircrafts allows automatic brake application after landing or rejected takeoff. An auto brake switch in the cockpit is used to select the different modes for automatic braking. Control of the system is performed by the auto brake module installed in MAU2. The automatic brake module is powered from DC bus 2 and commands both brake control modules to apply sufficient brake pressure to achieve the rate of deceleration required by the selected mode. To prevent unwanted auto brake activation, the ABM considers the following signals: throttle lever position, weight on wheels, landing gear down and locked, main landing gear wheel speed, and brake pedal position. The 5-position selector switch on the main instrument panel in the cockpit is used to select the auto brake modes. The following switch positions are available: rejected takeoff for maximum deceleration, off, low for low deceleration, medium, and high for high deceleration during auto brake. If the brake control system detects a brake fault, the auto brake selector switch springs back to the off position. According to the switch position, the ABM, which is an additional card in MAU2, gives pressure commands to both brake control modules to control the inboard and outboard brakes as during normal brake application. During auto brake control, the following protections are still available: anti-skid control, touchdown protection, and locked wheel protection. To prevent inadvertent auto brake application, several requirements have to be fulfilled to arm and activate the auto brake system. Landing auto brake can only be armed if the selector switch is set to low, medium, or high. The left and right weight on wheels indicate that the aircraft is in flight. The average wheel speed is below 60 knots. Pedal positions are all below 10%, and there are no brake control system faults. The landing auto brake will be applied if the landing auto brake is armed, the average wheel speed is above 60 knots, the weight on wheels indicates aircraft on ground for more than 2 seconds, and both throttle levers are in the idle position. The ABM calculates the landing auto brake application in relation to deceleration. The crew can reselect any of the 3 levels without disarming the auto brake. Landing auto brake will be disarmed if the selector switch is set to off or RTO, or any pedal position is above 10%, or any brake control system failure is detected, or either throttle lever is advanced beyond idle. The rejected takeoff auto brake will help the crew to stop the aircraft if it has been armed and takeoff is rejected. The rejected takeoff auto brake can only be armed if all of the following requirements are fulfilled. The selector is set to RTO. Left and right weight on wheels indicate that the aircraft is on ground. the average wheel speed is below 60 knots, and no brake control system failures are detected. The RTO auto brake will be applied if RTO auto brake is armed, the average wheel speed is above 60 knots, and both throttle levers are in the idle position. The rejected takeoff auto brake will be disarmed if the selector switch is set to off, low, medium, or high, or any pedal position is above 20% while wheel speed is above 60 knots, or any brake control system failure is detected while wheel speed is below 60 knots, or either throttle lever is advanced beyond idle during rejected takeoff auto brake application. If a failure in the auto brake system is detected, the auto brake fail caution will illuminate on the ICUS to indicate that normal braking has to be applied. Whenever one of the auto brake modes is armed, it will also be indicated on the ICUS by the following status messages: auto brake low armed, auto brake medium armed, auto brake high armed, auto brake RTO armed. If auto brake data is invalid or unavailable, 3 amber dashes will replace the indication. The fully independent emergency and parking brake system stops the aircraft in case of main brake system failure and applies the parking brake. The system is controlled from the actuating handle in the cockpit, which is mechanically connected by a push-pull cable to the emergency parking brake valve. The system is powered via 2 accumulators, which are fed by hydraulic systems 1 and 2. Pressure switches are installed in the system to give an indication in the cockpit if the emergency park brake is activated. With fully charged accumulators, the emergency parking brake system provides 6 full-stroke handle actuations or remains effective in keeping the aircraft parked for 12 hours. The center pedestal-mounted emergency parking brake handle controls the actuation of the emergency parking brake valve mechanically via a push-pull cable. The handle can be moved for 60 degrees between the stowed and brake full-on position to regulate the emergency brake. The handle locks at 60 degrees to set the park brake. The handle is released to allow travel back to the stowed position using a thumb-actuated button at the front of the handle. The connection between the handle and the emergency parking brake valve is accomplished with a ball bearing control cable. The push-pull cable consists of a moving core member held between 2 rows of ball bearings by 2 outer races, all contained in a flexible casing. The hydraulic fluid has to pass through hydraulic velocity fuses downstream of the emergency parking brake valve, equal to the ones described in the main brake system. The 2 emergency parking system fuses are installed in the wing stub. A shuttle valve installed on each brake will allow flow from the higher pressure source to the brake, either main brake pressure or emergency parking brake pressure. Pressure in the emergency parking brake lines is monitored by 2 pressure switches, one for the inboard brakes and one for the outboard brakes. If the pressure rises above 140 psi in either line, the parking pressure switch will close, and on the main instrument panel, the emergency park brake on light will come on. The pressure switches are installed in the rear wing to fuselage fairing, close to the wheel well. One 100 cubic inch accumulator is installed in each pressure supply line of the emergency parking brake system. The accumulators are installed together with a charging valve and a pressure transducer in the system-related hydraulic compartments in the left and right wing-to-fuselage fairings behind the wing. The accumulator is a cylindrical piston type with separated oil and nitrogen chambers. The pressure transducer will monitor the nitrogen side of the accumulator and will provide a low-pressure signal if the pressure drops below 1,200 psi. If both brake accumulator pressures are low and low pressure of hydraulic systems 1 and 2 is detected, an emergency brake fail caution will be illuminated. The actual accumulator pressure can be monitored on the MFD System Status Synoptic page. To activate the emergency parking brake, the handle in the cockpit has to be pulled up. Hydraulic pressure from System 1 and/or 2 is regulated in the emergency parking brake valve and directed through the hydraulic fuses and the shuttle valves to activate the brakes. If the handle is pulled up fully, it will lock at 60 degrees position, and the pressure is kept on the brakes. If the brake pressure is above 140 psi, the emergency park brake on light in the cockpit will illuminate. If the ICUS is in takeoff configuration, then a red Park Emergency Brake Set warning will be indicated. The emergency brake fail caution indicates that both hydraulic system 1 and 2 accumulator pressures are low. If one brake accumulator pressure is low, or inboard and outboard parking brake pressure disagree, the emergency parking brake fault will be displayed. The Brake Temperature Monitoring System, called BTMS, is installed to measure the actual brake temperature. This information is then provided as status information to the MFDs and for overheat cautions to the ICUS. Each brake assembly is equipped with one brake temperature sensor. The BTMS sensor is a Chromel-Alumel thermocouple that can be installed in one of two locations. One location is used to mount the sensor for the left-hand brake, and the second location is used to mount the sensor for the right-hand brake. The sensors are always in the upper position, allowing sensor replacement with the brake installed. The electrical signals from the four sensors are processed through I/O Module 2 in MAU3, which converts the BTMS voltage to a signal for display in the cockpit. The BTMS output that is processed in the I/O Module 2 of MAU3 is indicated on the System Status Synoptic page of the MFD. The MFD Synoptic page has two ways of providing temperature indication, numerical and pictorial. There are two brake temperature categories on the MFD, Status and Advisory. Temperature indication is green up to 251 degrees Celsius, which means that the brakes are able to absorb maximum kinetic energy. Advisory indication is shown in amber between 252 and 840 degrees Celsius, which indicates that cooling is required. If the temperature information has failed or is out of range, the arrow will disappear and the readout will be replaced by amber dashes. On the ICUS, the brake overheat caution will show up for brake temperatures above 690 degrees Celsius, and will disappear again if temperatures drop below 690 degrees Celsius. If the brake temperature rises above 749 degrees Celsius, the caution will latch and can only be unlatched by electrically powering down the aircraft. Note that the fuse plugs will melt in the main wheel, and inspections, according to the maintenance manual, have to be performed. Each landing gear of the Embraer E190 is equipped with a pair of wheels and a pair of tires. Each of the wheels is made of two wheel halves. A filling valve and a pressure relief plug is installed in every wheel. The main wheels are fitted with fuse plugs to prevent tire blowouts due to excessive brake temperature. The tubeless multi-retreadable tires are rated to 225 miles per hour. On each main landing gear, 2 multi-disc carbon brake assemblies are installed. The hydraulically actuated self-adjusting brake assemblies are equipped with quick disconnects for the hydraulic lines and 2 brake wear pins for visual inspection. The main wheel is a split web assembly made of 2 wheel halves, machined from forged aluminum. The 2 wheel halves are connected by 16 bolts with self-locking nuts and washers. 2 tapered roller bearings are installed in the center of the wheel, fully enclosed by bearing seals. A filling valve, or optionally a filling valve with an incorporated pressure gauge, is installed in the outer wheel half. A pressure relief plug, also located on the outboard wheel half, prevents overinflation of the tire. If the pressure rises to 365 to 435 psi, a metal diaphragm will break and release tire pressure. After activation, the plug has to be replaced. 8 quadruple-layer stainless steel heat shield segments are fitted to the inboard wheel half to protect the wheel and tire from excessive heat generated by the brake. In case of brake overheat, 4 fuse plugs in the inboard wheel half will melt at 193 to 204 degrees Celsius, 380 to 400 degrees Fahrenheit, and safely reduce tire pressure. 8 replaceable drive keys are bolted to the inboard wheel half to transfer the loads between the brakes and the wheel. A hubcap is installed on the outboard wheel half to allow drive clip engagement of the wheel speed transducer for the anti-skid system. The nose wheel is also a split web assembly made of 2 wheel halves machined from forged aluminum. The 2 wheel halves are connected by 8 bolts with self-locking nuts and washers. 2 fully sealed tapered bearings are installed into the wheel. A filling valve, or optionally a filling valve with an incorporated pressure gauge, is installed in the outer wheel half. If the pressure in the tire increases to between 365 and 435 psi, the pressure relief plug in the outer wheel half will release the pressure. The multi-disc carbon brake assembly slides over the main landing gear axle and onto a brake torque pin. The brake has the following main components: 1 pressure, 1 end plate, and 2 stationary discs, 3 rotating discs, a torque tube, a piston housing with 7 pistons, 2 wear pins, and a shuttle valve with quick disconnects. A brake temperature sensor is installed into the brake assembly at the top of the piston housing. The rotating discs are keyed to the wheel. The stationary discs are keyed to the brake torque tube. The brake assembly is interchangeable for left and right hand installation by rotating the shuttle valve and repositioning the brake temperature sensor. The carbon heatsink allows refurbishment by alternating different sets of carbon discs. Note, the refurbishment cannot be done on the wing. Each brake has 7 self-retracting and self-adjusting pistons. The self-adjusting mechanism compensates for brake disc wear and keeps the piston travel constant as the brake wears. The piston housing is attached to the torque tube. The cylinder sleeve is installed inside the housing. The spring-loaded piston moves inside the cylinder sleeve, forcing the insulator against the pressure plate during brake application. An internal spring and swage tube return mechanism provides precise adjustment of the brake. The mechanism adjusts to maintain constant clearance by deformation of the steel swage tube. A hardened steel swage tube is anchored in place at the end of the steel return pin. As the brake wears, the pistons are forced out. The piston pulls the swage tube past the swage, deforming the tube as it travels. This deformation of the swage tube progresses until the brake wears out. When brake pressure is applied, the shuttle valve will automatically allow flow from the higher pressure source into the brake assembly. The hydraulic pressure moves the 7 pistons against the pressure plate. The pressure plate compresses the carbon discs against the end plate. This compression causes friction between the rotating and stationary discs. When the hydraulic pressure is released, springs move the pistons back into position. Braking torque is transferred from the torque tube to the aircraft through the brake torque pin. The actual temperature at the center of the heatsink is sensed by the brake temperature sensor on top of the brake assembly. Brake wear is indicated by 2 wear indicators attached to the pressure plate. As brake wear increases, the pressure plate moves and pulls the wear pin to the wear indication bracket to indicate the worn brake. The Embraer steering control system is an electronically controlled and hydraulically actuated steer-by-wire system, operating either in the normal mode or in the free caster mode, also referred to as bypass mode. The system consists of the following main components. The steering handwheel, located on the left side in the cockpit, used for low-speed steering control. The pilot's and co-pilot's rudder pedals, used for high-speed steering control. And the disarming switches, located on the cockpit control yokes and on the left forward fuselage, used for active control of the steering mode by both pilots and ground personnel. The nose wheel steering control module, or NWSCM, electronically controls the steering hydraulic system. A steering manifold, located in the nose hydraulic compartment, provides and regulates hydraulic pressure to the steering motor attached to the nose landing gear main fitting. The steering control system is powered by Hydraulic System 2. The steering handwheel is attached to the left side of the cockpit. It incorporates a switch and a rotary variable displacement transducer. Pushing the handwheel down and turning it causes the aircraft to turn left or right. The RVDTs transmit the position of the handwheel to the NWSCM. The maximum steering angle possible using the handwheel is 76 degrees, and is limited further by the NWSCM as aircraft wheel speed increases. At taxi speeds from 40 to 100 knots, the steering angle will be reduced down to 7 degrees. Steering angle response to handwheel position is non-linear. Turning the handwheel from 0 to 40 degrees results in a steering angle of 10 degrees. And from 40 to 80 degrees results in a steering angle of up to 76 degrees. The steering input of the rudder pedals is sensed by 2 RVDTs installed in the cockpit control linkage. Rudder pedal position is transmitted from the 2 RVDTs to the NWSCM. Pushing the left or right steering pedal turns the aircraft left or right respectively. Steering deflection using the pedals is limited to 7 degrees left or right with weight on wheels. Whenever the steering handwheel is pushed down, the steering pedal mode is automatically disengaged. Transition from one mode to the other will be smooth. The steering pedal mode is automatically active after powering up, and if no failure in the steering system is detected. The steering motor is attached to the nose landing gear main fitting. It consists of two hydraulic cylinders with pistons attached to a geared rack, driving the circular gear on the main fitting. Hydraulic pressure from the steering manifold makes the steering motor move, and torque links transfer the torque from the steering motor to the lower part of the sliding tube and axle assembly. Two steering angle resolvers are installed on the nose landing gear, sensing the position of the sliding tube to provide a closed-loop steering control. One will feed back the position to the NWSCM control channel, the other one to the NWSCM monitor channel. The steering motor operates over a range of 76 degrees left and 76 degrees right. The steering motor will not operate beyond this range. However, the nose landing gear can be steered passively during towing over a range of 170 degrees left and right. The steering manifold is installed in the nose landing gear bay and incorporates the hydraulic system control components. The main components of the manifold are the servo valve, the solenoid valve, the bypass valve, the compensator, the anti-shimmy valves, relief valve, and anti-cavitation valve. A 50-micron filter is installed at the inlet of the manifold. A check valve will retain the fluid inside the steering manifold in case of loss of supply pressure. The solenoid valve is a normally closed, two-position, three-way valve. When energized, it moves to allow hydraulic pressure to reposition the bypass valve, allowing hydraulic pressure from the inlet to the servo valve. Depending on signals from the NWSCM, the servo valve directs pressure through outlet C1 or C2 on either side of the steering motor to move the nose wheels. At the same time, the opposite side is connected to return. The position of the servo valve is continuously monitored from the NWSCM by a linear variable displacement transducer, LVDT. Whenever the solenoid valve is de-energized, the bypass valve connects both nose wheel steering cylinder chambers hydraulically. This allows free castering of the nose wheels. The compensator provides a minimum pressure and fluid supply within the steering system in case of loss of supply pressure or free caster mode, necessary for the damping function of the restrictors and to compensate thermal effects. The anti-cavitation valves ensure that fluid return pressure is always available in the steering actuator chambers. This prevents cavitation during steering rates or oscillations. The anti-shimmy valves, or restrictors, provide a damping effect by preventing rapid fluid movements after, for example, a lateral shock or in the free caster mode. These valves, together with the anti-cavitation valve and the compensator, ensure effective shimmy damping in the free caster mode. The relief valves open to prevent overpressure in the system in case of excessive external loads to the wheels, for example, during aircraft towing with the system inadvertently active. The solenoid valve is a normally closed, two-position steering system can be disengaged manually using the pilot or co-pilot disarming switch on the control yokes or the fuselage disarming switch on the left-hand forward fuselage for ground handling. As long as the disarming switch on the control yoke is actuated, the nose wheel steering control module will switch to free caster mode. When the switch is released, the nose wheel steering control module will go to the hand wheel steering mode after re-engagement by pressing the steering hand wheel. The disarming switch on the forward fuselage is installed above the electrical ground connector. It is a guarded toggle switch to either operate in nose-wheel steering control module controlled steering in the engage position or in the free caster mode in the disengage position. Whenever the steering is disengaged, a steer off status message is displayed on the ICUS. On the left-hand side of the nose landing gear, a towing light box is installed. The towing light box green indication will illuminate when towing is allowed, and a red indication illuminates if towing is not allowed. The towing light function is operative when DC bus 2 or hot bus is applied, selected by a toggle switch on the towing light box. The NWSCM will bring up the red light to indicate that towing is prohibited if either the brakes are activated, the park brake is activated, or the steering system is active. If the green light is illuminated, towing with a tow bar or with a tow bar-less system is permitted. Please note that the maximum permitted angle for towing is 170 degrees to each side. The maximum allowable steering angle of plus or minus 170 degrees is monitored by an over-travel proximity sensor on the nose landing gear shock strut. In case the maximum towing range has been exceeded, a steering over-travel target will be sheared off. Via the over-travel proximity sensor, the PSEM-1 will detect the lack of this target. As a result, on the ICUS, the caution message LG no dispatch will be indicated. The steering is controlled through the nose wheel steering control module, called NWSCM. The NWSCM is installed into two slots of MAU2 and electrically powered by the DC bus 2, or by selection in the towing light box from the hot bus. The control module incorporates a control channel which commands the steering system and a monitor channel that communicates with the ICUS and the CMC for system status and failure indication. Whenever the air-ground system and/or the nose gear shock absorber proximity sensor indicate an aircraft in-flight condition, the solenoid valve is switched off. This prevents steering commands during gear retraction and flight. The NWSCM controls the servo valve and selector valve in the steering manifold and the lights in the towing light box. It receives feedback information from the handwheel unit RVDT, the two-pedal sensor RVDTs, and the three disarming switches, located on the pilot's and co-pilot's yoke and the forward fuselage. A servo valve LVDT sends servo valve position information in the manifold, and two position resolvers signal the actual steering position. In addition, parking brake pressure, brake activation, and aircraft on-ground signals are monitored by the NWSCM. Whenever the steering system is powered up, the pedal's steering mode is active. When the right-hand pedal is moved forward, the NWSCM senses this movement via the pedal sensor RVDTs and energizes the solenoid valve in the steering manifold. Hydraulic pressure from hydraulic system 2 can now move the bypass valve, and hydraulic pressure becomes available at the servo valve. The NWSCM then moves the servo valve to direct hydraulic pressure via the connection C1 to the piston of the steering actuator. The opposite side of the actuator is connected at the same time via the servo valve to return. The turning movement will be transferred through the torque links to the nose wheels. The NWSCM will receive the actual deflection information from the nose wheels and will limit it to 7 degrees. If the left-hand pedal is now pushed forward, the NWSCM moves the servo valve to the opposite side, connecting hydraulic pressure via C2 to the other side of the steering actuator and draining off the opposite side. The wheel will deflect to maximum 7 degrees to the left side. When the steering handwheel on the pilot's side is pressed down, the NWSCM will change to the handwheel steering mode by energizing the solenoid valve and allowing hydraulic fluid to the servo valve. An extended range of up to plus or minus 76 degrees nose wheel deflection is now available. If the handwheel is moved to the right side, the NWSCM will move the servo valve, and hydraulic pressure is available to move the steering actuator to deflect the nose wheels to the right. Via the position sensors, the NWSCM receives the position feedback signal to control and limit the steering. If the handwheel is released, the system will automatically go to the pedal steering mode. In case the nose wheels are still deflected, they will be smoothly moved to the pedal position related angle of deflection. If the aircraft takes off, the NWSCM will be switched off, and the nose wheel will be centered by the internal centering mechanism when the shock strut extends. When the steering system is deactivated, it enters the free caster mode. This could happen either by manually deactivating the system by one of the 3 steering disconnect switches, or automatically in case of a steering system failure. Through the bypass valve in the steering manifold, the hydraulic chambers of the steering actuator are connected, and the nose wheels may deflect due to external forces. The anti-shimmy valves, anti-cavitation valve, and relief valves guarantee shimmy damping in the free caster mode. The nose landing gear has an inclination of 8 degrees forward to center the nose wheels automatically in the direction of ground run. Towing with angles of up to plus or minus 170 degrees is possible in the free caster mode. Whenever a safety-critical failure, such as a servo valve failure or a power supply failure, is detected by the nose wheel steering control module, the nose wheel steering is switched to the free caster mode. On the ICUS, a steer fail caution is displayed when the landing gear is down. After this system disengagement, the nose wheel follows freely in the direction of ground run, and steering can be carried out by use of differential braking and/or by rudder commands. Reactivation of the system is only possible if the power-up built-in test is performed successfully. A steer fault advisory message will be displayed on the ICUS in the case of a degraded function of the steering system after a failure has been detected by the NWSCM and the aircraft is on the ground. The status message, steer disc, will be displayed if the steering system is disconnected, for example with the steering disarming switches. An LG no dispatch caution appears in case of a nose wheel steering over travel, proximity sensor evaluation module, PSEM, or weight on wheel system fault. For further fault investigation, the CMC has to be used, which will indicate the detected failure in detail. The landing gear position and warning system is used to provide landing gear status and failure information. The position and warning system has the following subsystems: the landing gear indicating system, the air-ground or weight-on-wheel system, and the landing gear warning system. The landing gear indicating system is controlled by 2 identical proximity sensor electronics modules. These PSEMs each make an analysis of the proximity sensors for the landing gear system. Ground spoiler system and aircraft doors. The air-ground system makes use of proximity sensors on the main landing gear and nose landing gear to determine whether the aircraft is on ground or in flight. The landing gear warning system forwards information concerning failures or abnormal landing gear configuration during landing to the ICUS. The landing gear indicating system processes the information coming from the gear lock proximity sensors and control lever signals to provide landing gear position indication on the right side of the ICUS display. Two proximity sensors which sense each locked condition, down-locked or up-locked, are installed at each landing gear leg. They are segregated in systems 1 and 2. The locking status from the proximity sensors and control lever positions are processed by PSEMs and sent digitally via ASCB to the ICUS. The landing gear indication system has the following components: 2 proximity sensor electronics modules, nose gear downlock sensors, nose gear uplock sensors, main gear downlock sensors, main gear uplock sensors, nose gear door sensors, and towing lights. Each PSEM is a dual-slot, single-channel MAU utility module. Each module is provided with 2 front panel and 2 backplane connectors. PSEM1 is installed in MAU1, powered from DC Essential Bus 1, and PSEM2 can be found in MAU3, powered from DC Essential Bus 2. PSEM1 receives inputs from the following proximity sensors: 4 nose gear door sensors, 1 nose wheel steering travel position sensor, 3 forward passenger door, 3 service door, and 4 forward baggage door sensors, 3 landing gear uplock sensors, 3 landing gear downlock sensors, 3 weight on wheel sensors, and 2 landing gear control lever switches. PSEM2 receives inputs from the following proximity sensors: 4 ground spoiler position sensors, 4 aft baggage door, 3 aft service door, and 3 aft passenger door sensors, 3 landing gear uplock sensors, 3 landing gear downlock sensors, 3 weight on wheel sensors, and 2 landing gear control lever switches. The PSEMs use the input signals to forward position information to the aircraft via the ASCB and LAN. The weight on wheel information is also sent to the flight control modules, the actuator control electronics, and the generic input-output modules. The proximity sensors are magnetic sensors, so that they may detect the presence of a metal target. Each sensor sends a signal to the PSEM when a target is near, and a different signal when the target is far away. On the nose landing gear, the following proximity sensors are installed for the gear indication system: 2 landing gear up and locked proximity sensors, to indicate that the gear is up and locked or not. They are installed into the uplock box of the nose gear. 2 landing gear down and locked proximity sensors, to signal the PSEMs that the gear is down and locked. They are installed at the upper locking stay and facing towards the targets of the downlock stay. The sequencing of the nose landing gear doors is monitored by 4 proximity sensors. 2 are installed on the left side and 2 on the right side of the nose gear wheel well. When the doors are closing, metal targets will end up in front of the proximity sensors. The proximity sensors send the signal to the PSEMs, 2 for each PSEM. If at least one of the 4 nose gear doors is not closed after nose gear uplock, or one of the forward nose gear doors is not closed after nose gear downlock, the landing gear nose door open caution message will show up on the ICUS. The message will also be activated in case of a failed nose gear door sensor or loss of valid ASCB communication from one or both PSEMs. The main landing gears are equipped with uplock and downlock proximity sensors. The 2 uplock proximity sensors per leg are installed in the uplock box to sense the gear when it is up and locked. The 2 downlock proximity sensors are attached to the lower locking stay. When the gear is down and locked, the metal targets of the upper locking stay can be sensed by the proximity sensors. The locking status from the proximity sensors and control lever position signal are processed by the PSEMs and sent via digital ASCB format to the ICUS. ICUS indication of the landing gear position consists of 3 colored symbols. From left to right, each box represents the position of the left, nose, and right landing gear. For the landing gear locked down, green circles enclosing a green word down are indicated. If the control lever is moved and the gears are in transition, amber crosshatches are shown. If the landing gear is locked in the up position, white squares enclosing a white word up are shown. A disagreement between the control lever position and any landing gear leg position for more than 20 seconds will activate the message, landing gear lever disagree, and the position in disagreement will change its color to red. In case of ASCB communication loss or invalid ASCB data from both PSEMs, the parameters will be defaulted to false condition, changing the indication to red and indicating the landing gear lever disagree message after 20 seconds. The weight on wheels indication system indicates whether the aircraft is in flight or on ground. It also makes use of the proximity sensor evaluation modules and 6 proximity sensors. 2 proximity sensors are attached to each landing gear shock strut to determine when the struts are compressed if the aircraft is on ground. The nose landing gear proximity sensors face the torque link. When the shock strut is compressed, the torque link folds, and metal targets are sensed by the proximity sensors. After liftoff, the shock strut will extend, unfolding the torque link and moving away the metal targets. This will end in the weight off wheel calculation. On the main landing gears, the proximity sensors are also installed on the shock strut facing the torque link and function exactly the same way as on the nose landing gear. The inputs of these sensors are calculated and combined by PSEM1 and PSEM2 and forwarded to the aircraft systems requiring weight on wheel status. The landing gear warning system will provide a landing gear voice message,
landing gear,
if at least one gear is not locked down and there is an intention to land the aircraft. The landing gear aural warning logic is processed in the Monitor Warning 1 and Monitor Warning 2 simultaneously, which are located on the NIC1, MAU1, and NIC2, MAU2 respectively. The landing gear aural warning logic uses the thrust lever angle, flap setting, and radio altimeter to define the intention to land the aircraft. When the aircraft is flying below 1,200 feet above ground level and 1 or 2 thrust levers are reduced with 1 or more landing gears not locked down, the aural warning landing gear will come up.
landing gear,
For dual engine operation, the message will come up if thrust lever angle is reduced below 45 degrees and in single engine operation below 59 degrees thrust lever angle. If the flaps are set to one of the two landing positions with at least one landing gear not locked down, the landing gear warning will be triggered independently of altitude or thrust lever angle position. In case of invalid radio altimeter signal, the warning will be released. This warning actuation due to an invalid radio altimeter signal is cancelable by pressing the landing gear warning inhibition switch on the main instrument panel. If pressed, a bar will illuminate in the switch to indicate that a cancel action was performed. The indication bar extinguishes if the thrust levers are advanced above 45 degrees with dual engine or 59 degrees with single engine operation. The bar will also extinguish in case the flap selector lever is set to landing configuration or if all landing gears are down and locked.